Hello friends, welcome to my channel. This is Isro question paper heat transfer part 2. The question is the radioactive heat transfer rate per unit area watt per meter square between two plane parallel gray surfaces, emissivity 0.9 maintained at 400 Kelvin and 300 Kelvin is Stefan Boltzmann constant also given 5.67 into 10 power minus 8 watt per meter square Kelvin to the power 4. This unit also sometimes they are asking. Here data given sigma is minus 8 watt per meter square Kelvin to the power 4. T1 400 Kelvin, T2 300 Kelvin. They asked Q 1 to 2. Emissivity both are 0.9. Q12 is heat transfer rate per unit area, so Q by A. It's minus 1. So first lower part will do here. Little bit calculative. 0.9 plus 1 by 0.9 minus 1. 0.9 plus 1 minus 0.9 square. 0.81. 2 minus 0.81. So it will come 1.1 by, it's 1.19, but we'll take 1.1 for easy calculation. So it's 11 by 9. Then Q12 by A. Put all the values. Here separately we will do this one. T1 to the power 4 minus power 4. Here we will do A square minus B square equal to A plus B into A minus B. So 400 to the power 4 is 400 square, then square. It's 400 square minus 300 square. So 400 square plus 300 square into 400 square minus 300 square. So 400 square plus 300 square is 500 square into again 400 plus 300 into 400 minus 300. So if you calculate that one, we will get 500 into 500 into 400 plus 300 is 700 into 400 minus 300 is 100. So finally Q by A is sigma T1 to the power 4 minus T2 to the power 4 sigma T1 to the power 4 minus divided by 1 by, both are same, so 1 by epsilon minus 1. Put the values 5.67 into per 8 into that. Already we got 1 by epsilon plus 1 by epsilon minus 1 is 11 by 9. So 11 by 9 into 500 into 500 into 700 into 100. 20406080. 10 to the power 8 cancel. 5.67 to make it 567 divided by 100. So 24. So it's 567 into 9, 7 by 44. Here 44, you make it 45. 9 into 5, then 5, 1, 1, 17, 5 into 3. So 113 into 7. 7 into 3, 21. 7 into 1 plus 2. Approximately 791 watt per meter square. So from option 791 nearby 812 watt per meter square. Heat transfer rate per unit area. Next is a spherical shaped vessel of 1.4 meter outer dia is 90 mm thick. Find the rate of heat leakage if the temperature difference between the inner and outer surface is 220 degrees Celsius. The thermal conductivity of the sphere is 0.083 watt per meter. It's spherical shaped vessel. So 1.4 meter diameter, 0.7 meter radius, minus 0.7 means 700 mm minus 90 mm thickness. We'll get 16 mm inner radius. 16 mm and temperature between the inner and temperature difference is 220 degree Celsius. Thermal conductivity K is 0.083 watt per meter Kelvin. So our formula is Q equal to del T by, already discussed in my previous video. For sphere it's 4 pi K R1 R2. Same question was asked in 2006 also. Already delta T given, R2 R1 K also given. Next only calculation. So Q equal to 4 pi K R1 R2 delta T by R2 minus R1. So it's 4 into pi into K 0.083 to R1 is 610 into R2 700 into delta T is 220. R1 minus R2 is 90. So 0.083 you divide 1000, it will become 83. Then we will start our calculation. 30, 2 plus 1, 30. This one cancelled. After that, pi by 9, approximately 3. So approximately 20. 20 into 83 is 1660. 166. 4 into 22 is 88. Here into 7. So divided by 10 to the power 3 for kilowatt and 10 to the power 3 to convert mm to meter. So we'll get around this one 3. So we'll get 1 point something from option 1 point. A not possible, B also not possible. C is nearby. So C is the answer. If you use calculator, then we will get that one. Next, with rise in temperature, thermal conductivity of air, A increases, B decreases, C remains constant, D may increase or may decrease depending on temperature. For air, this is very important for GATE, IAS, Isro, and for other public sector exams. If temperature is increases, then K of air or thermal conductivity of air increases. Thermal conductivity of liquid may increases, may decrease. It depends on the temperature. For solid, it decreases. And one more thing, thermal conductivity of gas is proportional to root 2 and inversely proportional to root n. This is molecular weight. And one graph is here. K versus thermal conductivity versus temperature. This is for solid, this is for gas, this is for most liquids, but sometimes it may decrease. For water the case is different. K and temperature for water. First it will increase, after certain limit it will decrease. So for liquid may increase or decrease, depends on temperature. So air here, gas, it increases. A is the answer. Next, the temperature distribution at a certain input of time in concrete slab during curing is given by T equal to 3x square plus 3x plus 16, where x is in cm, T is in Kelvin. The rate of temperature with time is given by alpha given 0.0003 centimeter square per second. It concludes. This is the case of unsteady state, one-dimensional heat transfer without heat generation. Your formula is del square T by, because one dimensional, 1 by alpha is thermal diffusivity, delta small t is for time. Here that again, this is the formula. On steady state, one dimensional without heat generation, heat transfer. T equal to 3x square plus 3x plus 16. Thermal diffusivity 0.0003 square per second. The rate of change of temperature with time, it's T. This one they asked, so we'll use that formula. T is 3x square plus 3x plus 16. So del T by del x, first derivative is 6x plus 3, second is 6. So we will put this value in that formula. Small t. So 6 equal to 1 by alpha is 0.003 into, in this question they ask rate of change of temperature with time, 6 into 0. Divided by 18 by 10 to the power 4. So we will get Kelvin per second. From option C is the answer. D is the answer. Little bit calculated. Next question. The heat flow rate through parallel walls of thickness L1, L2 and L3 having surface areas A1, A2, A3 and thermal conductivity K1, K2 and K3 respectively, with the first and last walls maintained at temperature T1 and T2 will be how much? That's based on direct formula. Delta T by RTH Q equal to so RTH is L1 by A1 plus L2 by A2 K2 plus L3 by A3 K3. So Q is delta T T1 minus T2 L1 by K1 plus L2 A2 K2 plus L3 A3 K3. From option it's A is the answer. Thank you friends for watching my video. Thank you.